Let's get started with continuity. So below are the criteria for the function f to be continuous at a point A. Now there's a lot of criteria and it's going to seem tricky at first, but it's really simple. After I explain these criteria, I'm going to explain what a continuous function looks like, and then I'm going to explain what discontinuities are. Okay, so we have three criteria for continuity. Note that if any of these criteria are not met, then we say that the function is said to be discontinuous at a point A. What is a point A? So A is just an x value. So A could be 7. We're looking at x is equal to 7. If A is -5, then we're concerned with x is equal to -5. Okay. A in this case is an input value or an x value. So let's take a look at the conditions for continuity. So f of a exists. What this means is that the function has a y value of f of a at x is equal to a. This essentially means that the function is defined at the x value of a. So if I say, okay, let's use x is equal to 7, what is f of 7? This should give you an answer. It should give you a y value. For example, maybe it could give you 10, -5, whatever the case may be. This must not be undefined. Okay, so if you were considering the function 1 over x and you said x is equal to 0, this is an example where you will get an undefined answer. So this is not what we want for continuity. We want there to be an output value. We want there to be a y value. Okay, so that's what it means when f is defined at x is equal to a. So that's condition 1 out of the way. Let's look at condition 2, and this is really, really simple. The limit as x approaches a from the left-hand side. Notice the little negative sign in the exponent position. Okay, so just to recap, that means the limit as x approaches a from the left-hand side of the function f of x, and that must be equal to the limit as x approaches a from the right-hand side of f of x. This is basically saying, or statement condition 2 is basically saying that the two one-sided limits must be equal to each other. Meaning, so let's draw a Cartesian point here, and here we have a function, and this is the other part of the function. So let's consider this x value here. Let's say that's x is equal to 3. As I approach 3 from the left-hand side, let's say it's approaching a y value of +1. It looks like that. So as I'm approaching 3 from the left-hand side, that is having a limit of +1. And as I approach 3 from the right-hand side, that also has a limit value of 1. So basically, the function from the left and from the right, or the limit from the left and the right, they must be approaching the same point. Okay, so the same value. And that's condition 2. Can't get any simpler than that. Let's go on to condition 3. So condition 3 is a bit tricky because it relies on condition 2, but it's nothing major. The limit as x approaches a of f of x. So notice that there is no plus or minus sign in the exponent position of the a. So in this case, we are looking at the full limit. And we know from previous lessons that the full limit can only exist if the two one-sided limits are equal. So let me just paint a scenario here quickly. If these two are not equal, let's say that's 5 and that's 7, automatically you cannot get the full limit, right? These are not equal, you cannot get the full limit. Okay, so you won't even need to check condition 3. You just have to stop at condition 2 and not even go to condition 3. But let's say that the full limit does exist, the two one-sided limits are equal. Then the last condition, we want the full limit to equal to the function value at a. So what we got from condition 1, let's say we had a function value of 10, right? And then the full limit, sorry, the left-hand sided limit and the right-hand sided limit were both 10. So the full limit is now equal to 10, and that's equal to the function value, which is 10, which we got from condition 1. Then we say that the function is continuous. Okay, so if 1, 2, and 3 are all met, we say that the function is continuous. Let's just read what condition 3 states. So the limit value at the point A must equal the function value at that same point. Okay, pretty self-explanatory. So that's all great. We have these three conditions, but it means nothing to us. These conditions really mean nothing to us if we don't know what continuity looks like, if we can't visualize it. So let me just give you an intuitive understanding of continuity. I have a function, I have a Cartesian plane here. If I say a function is continuous, whenever you hear the word continuous, what I want you to think about is a piece of string that has no breaks in it. So if I had to draw a function here, this function is what we call continuous, right? It's a long piece of string. There are no breaks in it at all. There are no holes in it. There are no cuts at all. The string doesn't look like this. It doesn't look like that, and it has a hole in it, and then it continues. You can see that this function has no breaks in it, so it's not as if like it's going like this, and then all of a sudden there's a random break, and then it's moving like that. No, it's just one nice, long, continuous piece of string. So when you think of continuity, think of a long piece of string with no holes or breaks in it. All right, so that's how we can visualize continuity of a function. Now, to understand continuity even further, we're going to look at discontinuity. So what happens when a function is not continuous or is discontinuous at a point? And that's really going to bring together the section of continuity. So let's look at discontinuity. And in general, there are three types of discontinuity. You may see them being called different things, but in general, there are three types of discontinuity. Let's look at the first one. The first one is what we call a removable discontinuity. Now, a removable discontinuity occurs when the first condition is of continuity is possibly violated. So the first condition is not violated, maybe it's not met. So f of a is undefined. Okay, so we could have a situation where f of a is undefined. Or we could have a situation where f of a is defined as, let's say it's defined as some number as 10, and we have the limit as x approaches a from the left-hand side of f of x, that's equal to the limit as x approaches a from the right-hand side of f of x. That's equal to, let's say, 5. So these two are equal, and that's equal to 5. Therefore, the full limit is going to exist. Okay, and x approaching a, and that's equal to 5. So notice that the two one-sided limits are equal, and the full limit then exists, and that's equal to 5, but it is not equal to the function value. So the full limit will exist in a removable discontinuity, but the full limit will not be equal to the function value at that point. Why? The function value at the point may be different from the full limit, or this may be undefined. Okay, so it may not be defined. So let's take a look at what this looks like on a graph. So here we have a removable discontinuity. I want you to take a look at x is equal to 2. That's where the discontinuity is situated. So as I approach 2 from the left-hand side, okay, we have a limit value of 1, and as I approach it from the right-hand side, we still have a limit value of 1. So the full limit is equal to 1. But I want you to look closely at this diagram. We have an open dot at x is equal to 2, meaning that the function is not defined at this point. So while the full limit is equal to 1, the full limit is not equal to f of 2, okay, because f of 2 is undefined. There's nowhere in this graph stating that f of 2 is equal to 1 because there is an open dot there. It could be the case that we may be given a piecewise function, and f of 2 could be defined to be minus 1. Okay, so the function value, f of 2, may be defined to be minus 1. So that's another possible case. So the key thing to remember in removable discontinuity is that the two one-sided limits will be equal, right? So the two one-sided limits will be equal. They will be approaching the same point. Therefore, the full limit will be equal. However, the full limit will not be equal to the function value at that point we are examining. Why? Either because the function value is different from the full limit, or because the function value is undefined. So that's how you know it's a removable discontinuity. And we call it a removable discontinuity because it's basically a hole in the graph or a hole in that piece of string. it's like a piece of that string has been removed and placed somewhere else. Or if the function is undefined, that point has just been removed completely. Okay, so that's what removable discontinuity looks like. We are specifically violating condition 3 of continuity, where the full limit is equal to the function value. All right, so that's a removable discontinuity covered. Let's move on to the next type. And the next type is an infinite discontinuity. Sometimes you hear it being called an asymptotic discontinuity. So this occurs when either one of the one-sided limits is equal to either positive or negative infinity, and that's going to mean there's an asymptote at that point x is equal to a, at that x value. Recall, we learned this when we have either one of the one-sided limits or both of them equaling to plus minus infinity, we have a vertical asymptote at that point x is equal to a, or at the line x is equal to a. That was something we covered in previous lessons. So that's another reason why this infinite discontinuity can also be called an asymptotic discontinuity. But let's examine the key feature of this discontinuity. I'll call it an infinite discontinuity. The key feature is that the limit as x approaches a of f of x is equal to plus minus infinity. So the limit from the left-hand side could be equal to plus minus infinity, or we have the limit from the right-hand side of that function equaling to plus minus infinity. Okay, so either one of these conditions, you could even have both of these conditions. Okay, that's going to cause an infinite discontinuity or an asymptotic discontinuity. And we can see it here. Okay, so as we approach, so this is 1, 2, 3, 4. So we're looking at 2. As we're approaching 2 from the left-hand side, the function is going toward negative infinity. And as we're approaching it from the right-hand side, the function is going toward positive infinity. So it's an asymptotic or infinite discontinuity. And we can see this. It's not as if the function is just a nice continuous piece of string. We have the function moving this direction and then in that direction. You can clearly see that there is a break in that string there. So that's an infinite discontinuity. Either one of the one-sided limits are equal to plus or minus infinity. One of them has to be equal to plus minus infinity at least. All right, that's the second one covered. Let's go on to the last one, jump discontinuity. And this one is really easy. This is where in the limit as x approaches a from the left-hand side of f of x is equal to a number. So it's not equal to plus or minus infinity. It is equal to a number. And we also have the limit as x approaches a from the right-hand side of f of x. And this right-hand sided limit also has to be equal to a number. So if these were equal to plus minus infinity, then we would say it is an infinite discontinuity. However, if we are dealing with these two and they are not equal, but they are equal, but each of them is equal to a number. For example, this one could be equal to 6, and this one could be equal to, let's say, negative 30. So they are equal to numbers, right? They are not equal to plus minus infinity, but they are unequal numbers. So the limit from the left is not equal to the limit from the right. That is what we get for a jump discontinuity. The function value, in terms of the function value, you don't have to pay too much attention to this in terms of a jump discontinuity. It could be defined, it could be undefined, doesn't really matter. The key thing in a jump discontinuity is that the left-hand sided limit and the right-hand sided limit are equal to actual numbers, not infinity, but they are unequal, okay? And the full limit won't exist. So the best way to see this is to actually look at a graph. Take a look at this function, and obviously you can see that there's a discontinuity at x is equal to 0. So as I approach 0 from the left-hand side, we have a limit value of -1. In that case, let's get rid of all this writing. In that case, the left-hand sided limit would be -1. And as I approach 0 from the right-hand side, the function value is approaching +1. So the right-hand sided limit is equal to 1. Now you can see that this is clearly not infinity, and that is also clearly not infinity. However, these two one-sided limit values are unequal. Therefore, that is telling you that this is clearly a jump discontinuity. Now, in terms of f of a, like I said, it may be defined, it may be undefined, but that's not really needed to classify this as a jump discontinuity. Okay, the key feature is this right here. Okay, and those are your three types of discontinuity. Now, let's go on to an example. So, take a look at example 1. It's asking you to discuss the continuity of the graph of f of x at x is equal to 2. So this is f of x, it's some linear function. It looks like it's x plus 2 at x is equal to 2. Let's classify the discontinuity, if any. So I'm looking at the graph, and I'm asking myself, is this a nice, continuous, long piece of string? No, it's not. There's a hole in the string. Therefore, it's not a continuous piece of string. This string or piece of string or a graph, if you will, has a discontinuity in it. And specifically, this discontinuity is occurring when x is equal to 2. Hence, that's why they asked us that in question. So take a minute, check if you can classify this discontinuity, and then I'll go through the solution. All right, let's go for the solution. So what I like to do in any continuity, discontinuity example is I like to go through all the conditions of continuity, and then at the end, I'm going to classify the discontinuity if any, sorry. So let's go through the first condition. We are concerned about the function value at x is equal to 2. So we write that as f of 2. If you look at it, the function has an open dot at x is equal to 2. Therefore, f of 2 is undefined from this graph. Okay, it's not like you have something here and f of 2 is defined to be, let's say, positive 2, or we had a situation where we had a closed dot on top there. In that case, f of 2 would be 6. No, I cannot see a closed dot on the line x is equal to 2. Hence, f of 2 is undefined. Next, the next condition, we're looking at the one-sided limits. So let's look at the limit as x approaches 2 from the right-hand side, sorry, from the left-hand side of f of x, and that is clearly equal to positive 4. And if we look at the limit as x approaches 2 from the right-hand side, okay, that is also equal to 4. So the function is approaching the same value from the left and from the right. So we will have limit as x approaching 2 from the right-hand side of f of x equaling to 4. And since these two one-sided limits are equal, the full limit also exists. Therefore, the limit as x approaches 2 of f of x, that's the full limit as x approaches 2 of f of x, that's also equal to 4. So, condition 2 is satisfied. Let's look at condition 3. F of 2 is undefined. However, the limit as x approaches 2 of f of x is equal to 4. So since f of 2 is undefined, we don't have a function value at that point. F of 2 is not equal to the limit as x approaches 2 of f of x because this value does not exist. Okay, it's undefined, basically. So let's take a look at this. You may have guessed what type of discontinuity this is from the graph when you sort, but I like to go through all the steps so you learn it. Notice that these two are equal, so the one-sided limits are equal, so this is characteristic of a removable discontinuity, and f of 2 is undefined, so f of 2 is not equal to the full limit. So just by looking at condition 2, the one-sided limits are equal, and the fact that f of 2 is not equal to the full limit, I know that this is a removable discontinuity. Okay, so removable discontinuity, let's write out the full word. Okay, at x is equal to 2. Okay, and that's how you handle this example